Determination of the stiffness matrix of the mechanical system when using the finite element method in the Excel. This is article number 4.6 of the book Mechanical Systems Calculations of the Marine Facilities. So, ladies and gentlemen, it is assigned the exercise to find the forces and the stresses, strains action in the truss. The truss consists of 3 rods. First, about nodes, we have one node to one node. The first node applied the force directed leftward. Force is 10 kilonewton. As the node is 2 supported, we have fixed support as well. This is a hinge. All nodes are hinges. And the rod between the first and second node, we denote as a first rod, element of. The rods are finite elements because we will talk about finding the forces, stresses, strains by the finite element method in the Excel. Second finite element and the second rod with the stiffness E product by A is the area of the transverse section of the rod and E modulus of the elasticity. So we have 3 rods of the same transverse sections of the same areas transverse and the same modulus of the elasticity. Second, between the nodes 2 and 3, the length is 4 meters. The first one 3 meter length. And at the end of the second rod supported by the sliding hinge. So this hinge allows the motion of the node 3, the horizontal motions of the node 3, but not allows the vertical motions of the node 3. And between the point first and the point third, we have the node, third finite element. And the sequence of the rods are 1, 2, 3, and the sequence of the nodes 1, 2, 3 as well. But the last one node, originally we consider the denotion of the numbers of rods counterclockwise. First, second from the point 1, from the node 1. And the last one we consider in the another direction from the point 1 to point 3. We obey the adopted indefinite one-shot rule that the number of the node, the minimal number, is a rod beginning and the bigger number is a rod end. As for the rod 3, this is the other direction of the denotion of the nodes. Okay, first of all, we have to consider the geometry. We have to assign geometry into the Microsoft Excel. A little bit previously in the article 4.4, we considered the finding of the another truss stresses, the strain forces in the elements of the other truss. We had the truss of 5 finite elements as well hinged and with the supports, the fixed support and the fixed hinges support and sliding hinge we had in the article number 4.4. And we used Microsoft Excel, very comfortable, very convenient software to decide the issues by the finite element methods. Now we will consider the opportunity to decide the issue by the Excel, Microsoft Excel software. So let me please to go to the Microsoft Excel file. Okay, this Microsoft Excel file. So first of all, we have to assign in the Microsoft Excel the geometry of the considered truss. The geometry. First, we have the table of the geometry of the truss. We have 3 lines as we have 3 finite elements. Each rod is finite element, first, second, and third finite elements. And first of all, we have to specify in the Microsoft Excel table the coordinates of the vertices of this truss. The vertices are nodes. Nodes are the points of the connection of the rods. So for the node number 1 is in between the rod number 1 finite element by 1. The rods are finite elements, so we have 3 finite elements. Number 1, between the nodes first and the second, we have 2 points. First and second, 2 points, the end, the first end and the second end. The first end coordinates are the abscissa 0 and the ordinata equal to 3 meters. 3 meters the height of the truss. So we have to assume that we use the Cartesian system, flat system coordinate with the horizontal axis x coincided with the axis of the second finite element between the nodes 2 and 3. And the second axis ordinata is vertical to the point 2. So in this coordinate system with the horizontal axis coincides with the second finite element horizontal, and the reference point we have 2. So the coordinates are the abscissa of the point 1 is 0 due to this is up from the point of the reference. This is 0 point. Just that's the notion of the node number 2. So 0, 0, and first point 0, 3. 0, 3, 3 is the h of the point 1 over the point 2. So the node 2 we have 0, 0 coordinates, and the point 3 we have 4, 0. 4, 0, like here we have for the second and the third, third finite elements, and we had at the beginning the one for the third, one coordinates 0, 3, 0, 3, 0 is coordinates of the point 2, 3 is coordinates of the point 1, 0, 3. Of the point 1, 0 is abscissa, 3 is ordinate of the point 1, and the same we have for third node at the end of the coordinates, the node number 3, the coordinates are 4 and 0. So now we download in the Excel the coordinates of the nodes of the mechanical system. In the nodes between each of couple of the nodes we have the definite one finite element. So next we have to define the lenses of the finite element. This is a sequence of finite elements, first, second, third. The lenses are the first finite element is in the lenses. We can use this formula. This is formula like a Pythagorean theorem. So we consider the square root of the of total of 2 squares. The first square is a projection of the finite element on abscissa axis. The second brackets is a projection of finite element on ordinate axis. So for the first one, x21 minus x2i minus x1i is the number of the finite element, x2 minus 0, the plus the y2i minus y1i, so it's I2 minus 3 minus square power 2 square is 9, square root is 3. So we have 3. After that, we can find by the Pythagorean theorem the lenses of all finite elements of the considered truss. Next, we have to find the geometrical characteristics of the trusses, the cosines of the inclination of finite elements to the abscissa axis. Abscissa axis, Alexey, please remind, abscissa axis is coincide with the rod number 3. This is a global coordinate system because in this coordinate system, by this geometry, we define the discrete model of the finite element method. This is characteristics of the discrete model. So cosine. Cosine is by the formula we have as a projection of the finite element on abscissa axis divided by its length. So we have the projection of the in the brackets here. We have the same here projection. For example, the first element on the abscissa axis is 0 minus 0. This is 0 divided by length by 3 meters. So we have 0 cosine. And the sine. Sine is the fraction in the numerator. We have the projection of the finite element on ordinate axis, and in denominator we have the length. So for the first finite element, we have the projection on the ordinate axis of the finite element. We have the 0 minus 3 0 minus 3 divided by 3, so we have minus 1. Minus 1 is the sign of the inclination of this definite one finite element relative the horizontal abscissa axis coincided with the second finite element. So for the second finite element, which coincided with abscissa axis, we have the proportion of the projection of the second finite element on abscissa axis, that is x2 minus x1. This is 4 divided by 4, so we have 1. The cosine and the sine, we have the projection ordinate axis. Due to this is horizontal finite element, we can define that due to this formula of the fraction of projection of this finite element, second one, I mean second, on the projection on the ordinate axis divided by the length is f as it is horizontal finite element, so we can find sine equal to 0 as well for the element number 1, 3. 1 is beginning, 3 is the end, so of the abscissa of end we subtract the abscissa of the beginning. This is 4. 4 divided by the 4 divided by the length of this finite element. The length we have 5, so we have the cosine 0.8 is the cosine of the angle of the inclination of this definite one finite element, and the sine as well we can have as 3 will divide to the length. 3 is 0 minus 3 is the projection of the finite element. This one inclined on the ordinate axis. The projection is minus 3. So of the ordinate of the end, we subtract the ordinate of the beginning. So beginning ordinate is 3. So the direction is from first to third point of this third number finite element. So we have sine minus 0.60. And the two last columns of the assigning of the geometry. This is not geometry characteristic. Yes, the last one is geometry. The area of the transverse section of the finite element equal to 0.0025 meter square meter. We assign the same for all finite elements at the same modulus of the elasticity. Now we did it in this is not a kilopascal. Yeah, this is kilopascal as well. The characteristics Fx, we have the force assigned in the kilonewton, so this is kilopascal, is very comfortable dimension of the elasticity modulus. So let me return this back. We define the geometry of the in the Excel of the considered truss, considered mechanical system. So let's apply for the decision by finite element method of the. We have to find the stresses in each of the finite elements in each of the rods, and we have to find the acting forces in the elements. So to do this issue, first we have to consider the stiffness matrices of truss elements. So we will do this for all truss elements for the, excuse me. For the first truss element, first finite element between the nodes first and the second, for the second between the nodes 2 and 3, and the third between the nodes 1 and 3. So this is a formula of the stiffness matrix in the local coordinate system of the finite element of force type. So let me please remind from the article number 4.4, we considered that in the mechanical system consistent of rods, usually we can define 4 types of the rod finite element. The first type, if the element is embedded by both ends. This is like for the frames, embedded by both ends of finite element. The second type of finite element is embedded by the beginning, and the hinge support on the other end. And the third type of finite element for rod mechanical systems like frames and trusses, the third type is the hinged support on the beginning and embedding at the other end of finite element. And the fourth finite element is the hinged supports at both ends of single span finite element. So they consider for the truss. For the truss, each finite element, each rod supported by the ends by the hinges. So we all have all hinges here. All hinges is first hinge, second hinge, and the third. Two hinges are supported by one second hinge supported is a fixed hinge. This is sliding hinge supported in one direction, vertical, but not in the horizontal. And this is a standard stiffness matrix for the finite element method. For definite finite elements, we used before we had decisions of the mechanical elements of the system. So we use the standard matrix for fourth type of rod finite element. This is the stiffness of rod finite element is E modulus of elasticity product by the transverse section square A divided by the length of the finite element. So for the first finite element, there will be index 1, E1, A1, we have the same, E1, A1 as for E3, A3, E2, A2, and A3, E3, A3, E3. But the elements has other lenses, 3, 4, 5 meters. So for the first one, when we substitute, we can derive the common factor out of the matrix. So the matrix will be 1, 1, minus 1. It's very easy to remember. For the fourth type of the finite element, we have this type of the stiffness matrix in the local coordinate system. For the second one, we do this by the product of this on the matrix. We fill using this products of these two cells of the geometry assignment of data divided by this one length. So for the second, we have as well stiffness matrix for the third finite element. All finite elements are of the fourth type. Next, we have to find the stiffness matrix of the finite element in the global coordinate system, because the goal is intermediate goal is to determine the stiffness matrix of all mechanical systems. So we have here all mechanical system stiffness matrix we have to define in the global coordinate system. Global is associated with total with integral mechanical system with the discrete model of the connection of the elements in the integral mechanical system. And this is a stiffness matrices we got. This for the first finite element, for the second one, and for the third in the local coordinate system. Local coordinate systems is systems each one coincides with the definite one finite element. So the definite element of the rod type, any type of the rods, like in the rod mechanical systems, like in frames and the trusses, each finite element we first assign the numbers of the beginning and the end of the finite element, and the local coordinate systems, the point of reference coincides with the beginning of the finite element, and the end of the finite element is the second point. We cross through the points the abscissa axis of local coordinate system, and to have the stiffness matrix of the finite element, each one, in the global coordinate system, global associated with the integral mechanical system, integral truss. We have to use the so-called cosine matrix or matrix of transformation from the local coordinate system to the global coordinate system. This is a cosine matrix. This we have for this definite class of flat truss consisting of rods. The cosine matrix is of two lines and 4 columns. This is 0, 0, 0, 0 elements of the third and the fourth element of the first row, and the first and the second element of the first row. This is zeros of the type of the cosine matrix for the flat trusses consisting of the rods, maybe for the frames as well. Not only for the trusses, but for the frame, any rod mechanical system flat. This is a standard type of the transformation matrix. But the cosines are the first two elements of the first row of the cosine matrix, and the last two elements of the second row of the cosine matrix we can take from the table of the geometrical characteristic assignment. We have the cosines and sines. For example, for the first finite element, we have the cosine 0, sine -1, sine of the angle of the inclination of the first finite element to the abscissa axis. So the sine is -1 because the angle of inclination to the positive direction of the abscissa axis. We have here, this is the beginning of the finite element, this is the end of the finite element. So it is angle of the inclination -90 degree, minus pi divided by 2. Oh, yeah, and so we have -1 is a sine of the inclination, and -1 is due to we repeated twice in two rows of the cosine matrix. The same for the second finite element. We have the this element coincides, this is horizontal one, coincides with the abscissa axis of the global coordinate system. The reference point of the abscissa axis we assigned point 2, and it goes rightward from the point 2, the abscissa axis, and the ordinate axis goes perpendicular through the point 1 of ordinate axis. So for the second one, as we have 0 angle of inclination, the cosine of the angle of inclination is 1, sine is 0, cosine 1, so sine is 0. This 0, 0, 0, 0, this came from these four element zeros of the cosine matrix. For finite element came from the type of the cosine matrix for this finite element. So we can take this 0 as the cosine of 0 angle of the inclination of the second rod. And for the fourth, the third finite element, we have the cosine of angle inclinations 0.19 and sine minus 0.6g, minus 0.6g, 0.8g, minus 0.6g. This as well, we have 0, 0, 0, 0, and 0.8g minus 0.6g, the cosine of the finite element inclining to positive direction of the abscissa axis. So, to do the definition of the stiffness matrix of each finite element in the global coordinate system, we have to transform. We have to transform to transpose. We have to transform the stiffness matrix from local coordinate system to global one, and to do that, we have to have as well the transposed cosine matrix too. How to do the transposition? In the Excel, we have the command. Command is transpose. So we have to select the place where we will insert the transposed cosine matrix. After that, we can dial in the address bar the transpose, the name of the operation. In the brackets we have to indicate the interval of the matrix, which one we have to do transpose. So we did, and we have the transposed matrix, transposed cosine matrix for each finite element of 3 we have in the considered truss. So this is the transposed cosine matrices for the first finite element, for the second, and for the third. And after that, we gradually, by two actions, have to find the product, the transformation of the stiffness matrix from local coordinate system to global one. We have to do by the product of matrices. First, we have to product the transposed cosine matrix on the stiffness matrix in local coordinate system. And after that, the result of products of these two matrices, the first one is very important, is the sequence of the product of the matrices. The first matrix we product, the transposed cosine matrix we product on the stiffness matrix, and we have this product of the transposed, this one, cosine matrix on the stiffness matrix, the second one. And after that, we have the result of the product. And after that, the result of the product, we have to product again by the by the cosine matrix, by just cosine matrix, not transposed. So third factor in the product of three matrices is just a cosine matrix. So first, transposed cosine matrix, next stiffness matrix in local coordinate system, and third, the cosine matrix not transposed, that's usual cosine matrix. And this product of three matrices in this definite one sequence give us the stiffness matrix in the global coordinate system. The stiffness matrix of the each one finite element is for the first one finite element, is for the second one, for the third one finite element in the global coordinate system. Global coordinate system associated with the integral mechanical system. And perhaps people remember that we considered the coordinates of the finite element of flat truss in the global coordinate system in the article 4.4. When considering the decision of the issue of finding the forces acting in the flat truss by the finite element method in the MATCAD computer algebra system. So now we do for the another one truss, but the same issue in the Excel system. And in the previous assignment, I mean in the article 4.4, we consider the example, what is the difference between the coordinates of the rod finite element in the local coordinate system and in the global coordinate system. For hingedly connected finite elements, that mean that we do not consider the bending moment and angular displacement in the finite element due to the hinges. The connections by hinges do not transmit the bending moment. So we have only the longitudinal force and the transverse action on the end of the finite element rod. So we have the two forces, two components of the force in the general coordinate system to the each end of the finite element. So first is component of the projection of the force action on the finite element on the abscissa axis of the global coordinate system. And the second is projection of the force of acting in the finite element on the ordinata axis of the global coordinate system. And if we consider this in the and this is for two ends of the for the rod finite element in the global coordinate system. So each we have two components of the force, each end, two ends, and the two components of each force application to each of two ends of the finite element. That's why we have the size of the matrix in the global coordinate system of 4. This is a two-dimensional matrix, yes, but two-dimensional of the size equal to 4. On the contrary, in the local coordinate system for the hinged hingedly connected finite element, we have only two components because each end experiences in the local coordinate system associated with this one definite fixed element. We have only with not the transverse displacement and the bending displacement of the ends of the finite element in the local coordinate system of associated with the finite element of truss. We have only the longitudinal displacement. Longitudinal displacement so of one end and of second end. So we have two displacements. And the size of the stiffness matrix in the local coordinate system consists of 2 by 2. The matrix size is 2 in the local coordinate system. But in the global, this is a matrix of size of 4 by 4. 4 by 4, that's why, because each end of finite element forces, we decompose in two components. So we have twice more components of the forces acting in the global coordinate system. And let me please remind that for the hingedly connected finite elements in the flat truth, we do not consider the action of the bending moments as the hinges of the connection of the finite element to other finite elements do not transmit the bending moment. So this could be for frames. If we would consider the frame, perhaps the size of the matrix of stiffness or in local coordinate system will be 3 by 3, and then the global coordinate system will be 6 by 6, as if for the frame. But it is not our deal. Today we consider the truss with only the stretching or compression of the finite elements. So, and gradually we found the stiffness matrix, the first one, transposed into the global coordinate system by consequent product of three matrices. First, we got the product of the transposed cosine matrix on the stiffness matrix in the local coordinate system, and we got this one, this intermediate matrix, and after that we got a product of this one, got previous intermediate matrix, like product of these two matrices. We got the product on the cosine matrix again, but not transposed, but usual cosine matrix. We have 4 by 4 global stiffness matrix of the bar finite element. Bar is the rod. So this was 2 by 2, and now we have 4 by 4. The size increases twice. We do the same for all three finite elements in the considered truss. And after that, we have to determine the global stiffness matrix of the flat truss. To do that, perhaps you remember that in the article 4.4, we do the so-called the matrix of the incidence, the matrix of the incidence of the knots displacement of the knots displacement of the truss of the mechanical system, and one hand, and another hand incidence with the displacements of the ends of the each finite element. So instead of that, we do not use here the matrix of the incidence, but we consider the common matrix as the total of three matrices. The question is how to locate the matrices, stiffness matrices of each finite element stiffness in the global coordinate system of the size 4 by 4 into the stiffness matrix of general of integral mechanical system, the truss of three finite elements. And first of all, we will assume what is knots of the knots of each of the finite element. The first finite element is between the first and the second knot. So we in the matrix of global stiffness matrix, to do the global stiffness matrix, we have to locate the stiffness matrix in the global coordinate system of this definite one first finite element in the cells corresponding to the first, and first is U1, V1. U1 is abscissa of displacement. V is the ordinate of displacement of the first finite element of the first, yes, of the first node. I'm sorry. This is abscissa of displacement of the second node, ordinate of displacement in the global coordinate system. This is abscissa of displacement of the third node and the ordinate of displacement of the third node. And to do that, we can do the copy of this matrix. We can do the copy like Control C, and we next can select the range of the insert of this matrix into the global stiffness matrix. For the flat truth, the range is indicated here for the corresponding the first and the second nodes, because the first finite element is between the first and the second node. So next we have to insert. We click the right button of the mouse, and next we can find this like one. Yeah, we have to insert only the magnitudes, not the formulas from the previous matrix to the considered one matrix to insert in. We do this insert. So you inserted only the magnitudes, not the formulas, because the cells is a result of the product by the function of the multiplication of matrices. We do not copy the formulas to the global stiffness matrix, only the magnitudes got. This is one of the options how to insert the to select the first range. Copy this to select the place to insert, and next the right button of the mouse, and the command to insert only the magnitudes of the from the first place, first range to the indicated range of the insert. The same we do for the second matrix, it's the second finite element, because the second finite element located between the nodes 2, so the abscissa of the displacement of node 2 in the global coordinate system, the ordinate of displacement of node 2 in the global coordinate system, that is the beginning of the second finite element and the end of the second finite element. So we have to make a copy of this one finite element stiffness matrix, second finite element stiffness matrix in the global coordinate system, and insert it for the definite range in the cells of the global stiffness matrix for the flat truss. And the same we have to do for the last one finite element, but for the last one is a little bit other way to do. So this is for the first, because last one matrix begins, last one finite element begins at node 1 and ends at node 3. So the first segment of the 4 magnitudes of the matrix of stiffness of third finite element in the global coordinate system, we have to introduce accordingly to the point, to the node 1, the beginning of the finite element. And the second segment, we have to introduce just the copies of the magnitudes. We have to introduce accordingly to the cells corresponding to the node 3. As well, this matrix is symmetric. This we can copy to here, and this part of the stiffness matrix in the global coordinate system we can repeat it here. So these places corresponding to the node 1 and the node 3. Node 1 and the node 3, abscissa and ordinata, abscissa and ordinata in the global coordinate system. So so it looks like the places separated, not so much important. After that, we can find the global stiffness matrix of the plane truss. How? We just have to find the total of these 3 matrices. The total of 3 matrices here indicated what's the formula of these 3 matrices. Total, and we do the matrix consisting of these 3 matrices. This is a stiffness matrix for the integral mechanical system. And after that, we have to consider as well the impact of the supports of the mechanical system, because let me please return a little bit again to the scheme of the mechanical system. This support not allow the displacement. So for the how to account the impact of the support onto the stiffness matrix, the second one maybe support. For the second one, we have to consider to find in the found stiffness matrix the point 1 to the direction, not available, the abscissa, the direction of the second node in the abscissa, the displacement of the second node in the direction of abscissa not possible. We dial 1. And all other cells in this stiffness matrix adopted with the supports, all other cells have to be 0, 0, 0, 0, 0, 0, 0, all zeros. another displacement of the node 2. We can account the not possible displacement along the abscissa axis. The node 2 is a fixed hinge, so the displacement along the ordinate axis is not possible as well. So we indicate 1. We specify 1 in the stiffness matrix, considering the conditions of the support in the second direction, ordinate direction of displacement, not possible of the node 2. This is supported node. So we specified 1 into the matrix of stiffness, and all other elements of this matrix of the column, of the same column, of the row of this matrix corresponding to this definite one cell of 1 have to be 0. 0, 0, 0, 0, 0, 0. And so very many zeros and only 2 ones. And the second hinge of the node 3, allows only the horizontal displacement. The horizontal displacement and the vertical not possible due to the impact of the support. The horizontal is along the abscissa axis. So for the point 3, we have to exclude the ordinate possibility of the ordinate displacement of the point 3. So to do that, we specify in the stiffness matrix U1 in the node of third node the ordinate displacement. We ordinate say V, so we have 1, and all other cells we have to assign 0. This is a matrix of stiffness with this one matrix of stiffness with the assignment of the conditions of the support. So in each node possible displacement if each node we indicate 1, 1, 1, and we for the two directions of the displacement abscissa displacement and ordinate displacement of the node number 2, this for 2, 2, 2, 2, yeah, and not in possibility of displacement of ordinate displacement of the point 3. So V3 not possible. We specify 1 as well in the matrix of stiffness, and for each ones, 1, 2, 3 ones, we exclude all other elements from the stiffness matrix. After that, to determine the displacements of nodes in the global coordinate system, we have to find the inverse matrix. In the Excel, we have the command. First, we have to select this matrix. Next, we have to dial in the address bar. We have to dial this command finding the inverse matrix, M inverse. And in the brackets, we have to indicate the range of the elements which are the matrix to be inversed. So this is a parameter of the matrix, like here we have. And we got the inverse matrix of the stiffness matrix after the account of the fixed supports in definite directions of the displacement of the nodes supported. So, and what is the displacements? Having we as well, we have to assign the vector of the external load. The vector of the external load we have to the point 1. To the point 1, we have external load. Directed leftward, so along the abscissa axis, but of the opposite direction to abscissa, the force is minus 10 kilonewtons, so directed leftward. So actually, as we indicate this vector, we probably would indicate like 10 kilonewton directed leftward, but this just not consider this minus a little bit, maybe error in the description. So, but in the vector description of vector description of the external load, the load vector, we indicate -10 leftward force applied to the first node. All other nodes are not loaded. We within the finite element method, we do not consider the distributed load acting on the finite elements because one of first steps when you use the finite element method, we have to transform the all load, distributed and local loads, to the nodal load. So all forces have to be applied to the nodes of the connection of the finite elements, and the elements themselves considered not loaded. This is approximation, of course, but if we have very small finite elements, this do not impact so much on the accuracy of determining of the forces and efforts acting in the discrete model of connection finite element in the global coordinate system, and not important for finding the displacements, forces, etc. if we transform the distributed load on the mechanical system to the nodal load. And having this load vector, we can find the vector of the displacements of node in the global coordinate system. How we will do that? We have to find the product of the inverse matrix stiffness, inverse stiffness matrix, this of integral mechanical system in the global coordinates. We have to multiply this onto the force vector, load vector of the in the global coordinate system, and this product is in the nodes displacement vector, the result of the product we have here, node displacement vector. So this is displacements of the nodes in the global coordinate system. Each cell is a product. So how to do that? We have to define the place of location of the node displacement vector. After that, we can in the address bar of the Excel just indicate the command. Command is the like this one. There's another place. Just the product of the matrices, multiplication of matrices, and then we have to select with definite one sequence because the sequence in the matrices product is important. So select the first range of the matrix, the first one in the product, the inverse matrix of stiffness in the global coordinate system of the considered flat truss, the good stiffness, with the account of the impact of the supported nodes of the truss. And the second range in the parameters of the matrices multiplication operation. The second is selection of the vector of the load. So the product we can have, the product will be displacements of the nodes of the considered flat truss found by the finite element method. After that, we just have to define what is the table of the result. The first table of the result is that we have to define what is the abscissas and ordinatus of the displacement of the ends of the finite elements in the abscissas and ordinatus of the beginning and at the end, the first and the second end of the finite elements in a global coordinate system. This is the 4 lines here in the one of the resulting tables, matrices in the MatCat. I'm sorry, in the Microsoft Excel. So to do that, let's consider what is the first end of the first between the first and the second end of the first finite element. The first end is 1, the second end is 2. For the 1, we have these 2 magnitudes we indicated here, and the end is not the 2 of the first finite element. For the first finite element, the end is 0, 0, indicated here. And gradually we fill the next column, the first end, as supported by the fixed support of the second finite element. Between the nodes 2 and 3, we have this 0, 0, and the next 2 of the second end, the abscissa and ordinate of displacement, we have the point 3, because we consider the rod between point 2 and point 3. And then we have the displacement, the abscissa and ordinate of displacement that copy here of the point 3, second end of the second finite element between the nodes 2 and 3. And the third finite element between the nodes 1 and 3, we have the first end is 1, node 1. We copy from the nodes displacement table here to this one. And the second end of the third finite element is the node 3. So from here, we substitute here to the cells, and we consequently got the matrix of the displacements of nodes of finite of nodes of the assigned truss in the global coordinate system. To do that, we consider the vector of nodes displacement got by the product of the inverse stiffness matrix onto the vector of the external load. This due to the canonical equations of the, like for the displacement method look like. And next we have to come back to local coordinate system. To local because we have to find the deformations of each of finite element to find the stress acting on the finite element, to find the force. We have to find the assignment to find the stress acting on the finite element and to find the force. To transform this from the global coordinate system of the displacements of the ends of finite elements, which at the same time is the nodes we got in the global coordinate system before by product of inverse matrix of stiffness on the vector of the acting external load. So we can use the transform as in the local coordinate system, the displacements of the ends of finite element, we can find by the product of the cosine matrix, not transposed, because we use a sequence of the product of matrices when we went from the local coordinate system to the global one. We need to do that for the global one because the stiffness matrix of integral mechanical system we define in the global coordinate system, and after that we have to return back because we have to find the forces acting in each finite element, and we have to adopt found displacements of the node of the discrete model of the integral mechanical system to the local coordinate system of each of the finite element. To do that, we have not use a product of three matrices as we did when we did transform from local coordinate system to global one, but just only the product on the cosine matrix of the matrix found in the global coordinate system. This is matrix found in the global coordinate system of the displacements of the ends of the finite elements, the rods of the considered truss, and by product in the by the product of the cosine matrix of each finite element on the matrix of the vector of the displacement of ends in the global coordinate system of each finite element, we can find the first end finite element displacement in the global coordinate system, the two cells, the second end of the finite element between the ends 1 and 2, this first finite element. We after the product of the matrices, we can find the magnitudes of the displacements of the ends of rod finite element of the considered truss in local coordinate system of each finite element. So we can see that what is the displacement in the local coordinate systems coincided with each finite element. The reference point of local coordinate system usually coincides with the beginning of the finite element at the end of the finite element. As a second point, to which the abscissa axis of the local coordinate system goes from the reference point. And after that, we can find the deformation. The deformation, by the formula, this one indicated here, is the difference of the displacement of in the local coordinate system of the end of the finite element and the displacement of the beginning of the finite element. The first end and the second end, and second end of the finite element and the first end of the finite element, and divided by the length of finite element. The displacements of the end and of the beginning of each finite element we take from the previous one matrix after having this by the product of the displacement and global coordinate system displacements as a second factor. But at the first we used the cosine matrix of each finite element. And for we got the matrix of the displacement of the finite elements and local coordinate system, the ends, and the deformation is like we from the displacement of the end in local coordinate system subtract displacement of the beginning, and the result divide by the length of this one finite element. This is the first finite element, and the length of the finite element we take from the geometry matrix of the initial data assignment. This is the length of finite element. So for the first column we divide by 3, for the second divide by 4, and for the third we divide by 5. Yes, and those we got the deformations. Deformation is the like strain, the relative displacement of the end of finite element relative the beginning of the finite element relative displacement, and divided by the length of finite element. So the specific magnitude of the deformation. And the deformation of finite element for the rod finite element, especially for finite with not distributed load along the each finite element within the frameworks of the assumptions of the finite element method, we assume that the deformation equally the even distributed along the length of the finite element. So this deformation distributed at each point of the finite element. First, second deformation element distributed along each length, and the third finite element deformation. So to find the stresses, we have to, in accordance with the Cook law in the mechanics, we have to find the product of the deformation by the modulus of the elasticity. Modulus of elasticity we have here. Modulus of elasticity in the first table is assigned equal for each finite element considered, each 3 elements of the considered truss. And to find the force, we have to multiply the stresses acting in each finite element by the transverse square of each finite element. To have that, we got the forces at the product of the stresses by the area of the transverse section of the finite element. So this is what we have to find by the Excel use of the Microsoft Excel for the decision of the issue of finding the forces action in the elements of the flat truss hinged rod mechanical system connected by the hinges. And using the in the Microsoft Excel of finite element method, when we combine within the definite discrete model of the before had decisions of the deformation stresses strains of the each finite element, and to do that we used the before had decision as for example the matrix of the stiffness of the like that matrix of stiffness of the rod finite element of the force type hinged by both ends available in the mechanics. So now let me return back to the presentation and briefly repeat what is the sequence of finding in the Microsoft Excel of the decision of the flat truss by the finite element method in the Microsoft Excel. So Okay. So first we consider the assigned truss. We specify the coordinates of the assigned flat truss in the table of the data as coordinates of the beginning and the truss first end and the second end of each rod. Each rod is each finite element. We define that the sequence is 1, 2, 3 of the finite elements of rods of the same area of transverse section of the same material, the elasticity the same. We have here, and besides, we got by this initial data the geometric characteristic of the finite element of the considered flat truss as length of each finite element in cosine of the inclining of each one finite element to the positive direction of abscissa axis of the global coordinate system. In the global coordinate system, we assume that the abscissa reference point of the coordinate system is point 2 of the assigned truss, and the abscissa axis goes on the right and crosses the point 3, and the abscissa of coordinate is perpendicular and goes from the point 2 reference point to the point 1. Next, we have to define what is the stiffness matrix of each finite element in local coordinate system. As we have fourth type of finite element, we have the standard decision of what is the stiffness matrix of the rod finite element in the mechanical system of fourth type. For the flat state on the plane, we have this formula to find. We can stiffness matrix in local coordinate system. We can derive the common factor out of the brackets of the matrix, and we have this matrix of the stiffness in the local coordinate system. After that, we do for the next transformation from the local coordinate system associated with each one finite element, we have to do transform to the global coordinate system. To do that, we have to consider the cosine matrix for this is of the usual type. For the flat approaches we used, the cosine matrix is 2 zeros in the first row of the third and fourth columns, and the zeros in the second row for the first and the second columns. And these two magnitudes of the cosine of the angle of inclination for each finite element we take from the geometry description in the first table of the from the description of the geometry of the finite element for second rod consequently. So now we have the cosine matrix. Just to do the command, this is the how it looks like. The first two factors, the factor multiplied by the matrix is a matrix of stiffness in local coordinate system, and each product on the vector of the displacement of the finite element and local coordinate system gives us the forces acting on the end of the finite element of local coordinate system. And this looks like the canonical equation of the displacement method in the structural mechanics. And this is standard for types of the rod finite element in the mechanical system. So we consider the rod finite element of the fourth type supported by the hinges by both ends. So as we consider the truss, if we would consider the frame, there will be could be the first type of the finite element. The first type finite element is embedded by both sides, and the second type embedded by the beginning and hingedly supported by the end of the finite element. The third type is the finite element hingedly connected on the beginning and embedded by the end. And the fourth type of the finite element, like our definition show, the hingedly connection of both ends of the finite element. The size of the matrix of stiffness for the flat mechanical systems could be of 2 element 2 by 2 or maybe 3 by 3 if we will consider the bending as well. For the truss is characteristic only the stretch and compression of the finite elements, the elements of the truss, the rods. So if we would consider the frame, for example, there could be three elements of the matrix of stiffness of in the local coordinate system, because the third will be the stiffness due to the bending of the finite element, rod finite element of the mechanical system. If we would consider the frame, but in our case, we consider the truss that is the rods of the truss connected by the hinges. Hinges do not transmit the bending mode, so we have only the forces transmitted by the hinged connections of the mechanical system. And the two components of forces, we have only longitudinal in the local coordinate system component and the transverse component. So this are that is why we have the stiffness matrix in local coordinate system for the hingedly connected number 4 type rod finite element. We have only this standard decision of the matrix of stiffness of 2 by 2 elements. So next we explain how we can find the stiffness matrix in the global coordinate system of each finite element. So first we have to find the product. This is transition, the kind of transition from global coordinate system to the local one. This is how we do that. We do at the end of our issue. At the end of our show, when we got the displacements of the ends of the mechanical system, the global coordinate system, and we have to find finally the deformation. To do that, we have to have the displacement in local coordinate systems. So from the global coordinate system, we go to the local coordinate system by the use of the product of the matrices of the displacement. This in the global coordinate system, but this is local coordinate system. This cosine matrices, how to do the transform. This is the first factor of the transforming the stiffness matrix from local coordinate system to the global coordinate system. Almost all of the calculus within the frameworks of the finite element method is geometric combining of the decisions we had, of the mechanical decisions we have for the finite elements to the decisions of the decision mean finding the stresses, strains, forces, displacements of the mechanical system. And that's why almost the lot, maybe 90% of our calculations is with use of the matcat or with use Excel, is the calculations of the matrices of the geometry of the connection of finite element into the discrete model. And we have to do the transforms from local coordinate systems of vector algebra, associated local coordinate systems with the finite elements each, to the global coordinate system, which is associated with the integral mechanical system consisting of finite element by them connection within the frames of the discrete model. So this is the intermediate matrix of the product of the stiffness matrix of finite element number I. I is the number of finite element. 1, 2, 3. We have 3 finite elements in the local coordinate system by the transposed cosine matrix. We have the intermediate matrix. After that, we have to multiply this intermediate matrix on the transposed cosine matrix, and we will have the stiffness matrix of finite element in the global coordinate system. So this is the second factor. The first two factors we multiplied in the definite one sequence in the previous matrix here, and we have to have the second one product, and this is a general formula transition of truss finite element stiffness matrix from local coordinate system we got originally from the local coordinate system to the global one, and this is transposed matrix of the transition. We did the same, the transition from the global coordinate system to local one, from local to global. In the issue, we considered in the article 4.4 by the matcat computer algebra system. The multiplications of matrix we do by the available in the Microsoft Excel command mult and in the brackets. So we have to select first the place which in we will insert the result of the matrices product in the parameters, and after that we have to indicate the range of the table in the Microsoft Excel, which from we have to take. I'm sorry. Yeah, and next in the parameters we have to indicate two matrices in the definite one sequence, which one we have to product. This is the first matrix, this is the second matrix in the product. And in the Microsoft Excel, originally we got the decision of the products of two matrices, the first, the intermediate matrix, and next we decided about the final result by the product of the previously one intermediate matrix onto the matrix of cosine again, and inserted here this into the template we got originally, the template of the location of the elements of the stiffness matrix of the integral mechanical system in the global coordinates. So we have the template and we inserted the product of three matrices in the first one range. After that, we do determine for the second finite element, which is between the node 2 and 3. We do the same. We had the stiffness matrix local coordinate system. We have the cosine matrix for second element. We have the transposed cosine matrix. I'm sorry. And we got the product of the stiffness matrix on the transposed matrix on the stiffness matrix. We got the product of transposed cosine matrix on stiffness matrix local coordinate systems, and next we had the product of the got intermediate matrix to the cosine matrix for the second element, and we inserted in the cells of the template got for finding the stiffness matrix of the mechanical system and the global coordinate systems. So this because the second element is between the node 3, node 2, this abscissa of displacement of node 2, this ordinate of displacement, and the maybe abscissa of the force applied in the node 2, and ordinate of the force applied. This abscissa and ordinate of the node 3, the node of the connections of the second element to other parts of the mechanical system. And the same we do for the third finite element as well. We have the stiffness matrix for finite element, the cosine matrix. We have the product of the this matrix on the cosine matrix, and of that we on the transposed cosine matrix, and next we get the product of the transposed cosine matrix by this cosine matrix. The sequence of the production of three matrices defined here. We obey this cosine matrix, transposed cosine matrix. So for the third finite element, we did this all. And it is a little bit different, the location of the results of the finding the stiffness matrix for third finite element location in the template when finding the stiffness matrix of the in global coordinate system of the mechanical system, the truss. So we have to obey the rule that the third finite element is between the first and the third nodes. So we have to use the segment of this matrix got of the stiffness of third finite element in the global coordinate system. This is a matrix. We have to take this first segment in the cells corresponding to the first, the beginning of the first node, the beginning of the third finite element in the considered mechanical system. And the second part, the second segment is from the stiffness matrix of third finite element in the global coordinate system. We have to copy to the cells of the template when we do the stiffness matrix of integral coordinate system on the global coordinates. This is 2 inserted because the end of the third finite element is the node 3. So we used only the cells for the node 1 and node 3 as the ends. The first and the second end of the third finite element is the nodes 1 and 3. And this is as well symmetric for node 3. We have this one copied to here, node 3, due to the concepts of the reciprocity of the stiffness matrix. This is same the copy of the first segment of this matrix. So anyway, we got 2 partial field templates to have the stiffness matrix of integral mechanical system and the global coordinate system. We first found the stiffness matrix and the global coordinate system of each finite element. Next, substitute in the template with the size of the components of the displacements for 3 nodes, because we're talking about the discrete model, and the displacement of the discrete model is the displacement of the nodes of the connection of finite element in the discrete model. So we have for the first finite element, for the second finite element, and for the third finite element. And next we have the total matrix. When we do find we add all 3 matrices to each other. The 3 matrices of the templates with the absence of definite elements of the installed matrices of stiffness of each finite element in the global coordinate system to definite places in the template. We have total of these 3 partially filled templates. And this is the stiffness matrix of the mechanical system in the global coordinate system. After that, we have to account the impact of the fixed nodes. We have the second fixed node by the fixed hinge, and the second node supported by the fixed hinge. And so it not allows the displacement in the direction abscissa and ordinata. And we have third node supported by sliding hinge. It not allows the displacement of the node along the ordinate axis only. So in the directions of the nodes, which is not allowed the displacement of the ends of the mechanical system, the displacement nodes of the mechanical system at the ends of the finite elements, we have to specify just one in the stiffness matrix of the mechanical system, the global coordinates. Specify 1, 1, 1. This is just only the cells corresponded the influence of the supports, which directions the corresponded the definite one, abscissa or ordinata direction, or ordinata here, direction of the node 2, and node 3, which not available the opportunity to have the displacement in these directions, definite one nodes. And all other cells of the columns, the same columns, and the rows, when which one we specify one not allowing the displacement, we have to specify zeros. So we exclude the opportunity of displacement of these directions for definite nodes. And the remaining matrix we need to find for the God matrix of the stiffness of the mechanical system in the global coordinate system, considering the impact of the support on the mechanical system. To this matrix, we have to find the inverse matrix. The inverse matrix we got by the command available in Microsoft Excel. To find the inverse matrix, we select the place to insert the matrix, and we dial in the address bar of the Excel to find the inverse matrix. And we have the inverse matrix of stiffness matrix in the global coordinate system, considering the action of the support will not allow the definite displacement in the abscissa or ordinate directions, or definite nodes, a second or third node. After that, to find the displacement of node of the mechanical system, we must to generate the vector of the external load. We have only one external load applied to the point 1 and directed leftward. So we have minus 10 kilonewton, all other zeros. And the product of the stiffness matrix inverse on this vector we do by the, we select the range of the insert of the result of the product. Next, we used the command multiplication of the matrices. So vector is a one column matrix. We multiply this stiffness matrix onto this column matrix. And we have the matrix of the displacements of the nodes of the discrete model of the mechanical system, that is the rod truss. And after that, we have to redefine the displacements of the nodes of the mechanical system got this displacement of nodes abscissa displacement, ordinate displacement of first node abscissa and ordinate second node is supported, not displacement not available. And the abscissa displacement of the third node is a sliding hinge. So the abscissa displacement possible, horizontal, vertical not possible. So after that, we define the displacements again in the local coordinate system. So as for the first and the second end for each finite element, the first one between the node 1 and 2, the second one between the node 2 and 3, the third one between node 1 and 3, we just copied the displacement of definite one node to the displacements of the end of the mechanical system. For example, the second end is here is of the first node is of the first finite element is the second end is a node 2. So the here we displacement have as a for node 2 abscissa and ordinate we have 0 displacement because this is supported. Node 2, the second end of the first finite element. For the second finite element as well, the beginning is the first end is the supported node 2. So it has, as we got previously, 0 displacements, and we just indicate this here, the 0 displacement, and the end has the displacement of the second finite element, second between the node 2 and 3. The end is the node number 3. The node number 3 is possible the displacement horizontal along the abscissa axis. We take it from the previously had decision when we multiply the inverse matrix of stiffness of mechanical system on the matrix of the external load. And for the same for the third node. And after that, we have to transform these displacements of the nodes of the ends of the finite elements of the first, second, and third finite elements. Displacement we have here u, v, abscissa and ordinata in the global coordinate system. We have to transform this in local coordinate system associated with each one finite element. Local coordinate system is associated when the reference points usually coincides with the beginning, the first end of the finite element, and the direction of the abscissa axis goes along the finite element to the second through the second end of the finite element. So we have other cosine matrices for each finite element, and we have to find, due to the formula, the transformation of by the product of the cosine matrix of each finite element to the vector of displacement of the nodes uv, as well as we have here, of each finite elements in the global coordinate system, and we will have the displacement in local coordinate system. And we got the displacements in local coordinate system by this way. This last two rows of the considered matrix on the figure 4.6.17a. After that, we have to find assignment to do the assigned assignment and to find the deformations, stresses and strains. The deformation we find as by the formula of the displacement of the end of the rod minus displacement of the beginning of the rod divided by the length of the rod. This rod is finite element number I. So for the first finite element between nodes 1 and 2, we got deformation as we subtract from the displacement of the end and local coordinate system, we subtract the displacement of the beginning. And we divide by the length of the forced rod. The forced rod, we have the length, as remember, maybe equal to 3. So we have 3 lengths in the table of the geometry of the assignment. The lenses are 3, 4, and 5 for fourth, second, and for the third finite element. And for the second one, we subtract from the end displacement the 0 is the displacement of the first end, divide by the length of second 4 element equal to 4, and got minus 0.019. And the third finite element we subtract from the in the local coordinate system displacement of the end minus the displacement of the beginning of the third element divided by the length of third element, as I remember, equal to 5, the length from the first table, and we have this size of the deformation of this deformation is even distributed by the length of each finite element due to in accordance with the concept. So the finite element method, the forces, we do not consider the distributed forces when we calculate the deformations of finite element. Distributed forces in each finite element, besides of the forces of the element deformation. The first step of the use of the finite element method is the transformation of the all distributed load action on the mechanical system to the forces applied to the nodes of the connections of the finite elements within the mechanical system within the discrete model of the mechanical system of the connection of the finite elements. So having deformations, we can find stresses. To find stresses, we have, in accordance to the Gauge law, we have to multiply the deformation on the modulus of the elasticity, and we have the stresses. And after that, if we multiply the stresses on the transverse section area of the each finite element, we have equal transverse section area. When we do the product, we can find the forces. So this is the sequence of the decision of the issue to find the stresses, forces, deformations of the flat mechanical system. We consider the flat truss by the use of the Microsoft Excel. If we do not have the MATCAD computer algorithm system, which is, in my opinion, just a little bit more convenient to use for these definite one decisions. But the Microsoft Excel is widely distributed and available at any working place, as I understand that. So questions and comments. The required initial data for determining the displacement of truss nodes and forces in the rod elements and of the truss using the finite element method in the Excel program. The same initial data as when we use the finite element in the not in the Excel, but in other software, maybe in the MATCAD. The required data is the geometry of the mechanical system. The geometry, I mean the coordinates of the nodes of the connection of the finite elements if they rod a mechanical system like truss or maybe frame. We have to know the coordinates of the connection of other finite element within the discrete model of the mechanical system. Besides, we have to have the external load and the characteristics of the elasticity of each finite element and characteristics of the transverse section of each finite element, or instead of the use of the characteristics of elasticity, like modulus of the elasticity and transverse section square, we can use the more general characteristic, like the linear stiffness of assigned could be linear stiffness of each finite element, etc. This first we consider the geometry and the mechanical properties of the assigned, and external load assigned, and to process with that in the table of the initial data. 4.6.2 determination of the Excel table of the length values of hinged and numbered truss rod elements, the direction cosines and sines of truss section in the global coordinate system, the linear stiffness characteristics We can use the calculations of the geometry determine the length of each finite element by, for example, the Pythagorean theorem. We can first we find the projections of each finite element onto the coordinate axis. Next, we use the Pythagorean theorem to find the using the projections got to find the length of each finite element. After that, we can find the cosines of the inclination of each finite element to the abscissa axis of the global coordinate system. The cosines equal to the fraction, the proportion of the projection of finite element on the abscissa axis, length, finite element length of the abscissa axis. Choose the length of the finite element sine. Accordingly, is the fraction in the numerator. We have the projection of the ordinate axis of the length of the finite element, and the denominator we have the length of the finite element. 4.6.3 stiffness matrix of a finite element rod in a local coordinate system with local stiffness matrix in an Excel table. We can define the stiffness matrix. It can be for the flat state on the, if we consider the flat truss as we did. This can be of size of 2 by 2, the stiffness matrix. In other case, if you consider, for example, frame with not hinged connection, but with rigid corners of the connection of the finite elements, that is the rods of the mechanical system of the frame in case of the frame. So the stiffness matrix can be 3 by 3 because for the frame we have to consider as well the bending, because rigid corners transmit the bending moments too. As for the truss, we have the hinged connections of the finite elements. The hinged connections do not transmit the bending moments. So in our case, we have the stiffness matrix only of the size 2 by 2, and we have the standard type of the stiffness matrix, like in the considered case, independence on type of finite element. We have in the truss finite element of force type. Force type is the single span finite element supported by hinges at two ends of the finite element. So we have the beforehand got decision what is. It's very simple, consisting of 4 elements, and this is just the product of the linear stiffness of matrix on the matrix of just only units, one by diagonal and by another diagonal -1. The product is the stiffness matrix of the finite element of a force type in the flat state. 4.6.3 stiffness matrix of a finite element rod in a local coordinate system with local stiffness matrix in an Excel table. Yeah, this just what I told a little bit before. This is standard decision, and considering the assigned data of the elasticity and the transverse section of the element, or maybe the data on the linear stiffness of the element of the mechanical system, and considering the type of finite elements connected, is it 1, 2, 3, or 4 type of finite element, of rod finite element, dependence on what is the mechanical system, is it frame or truss. We can find the stiffness matrix. 4.6.4 matrix from form of the equation relating to acting forces and deformations. Looks like the equation looks like the canonical equation of displacement method. The difference is available that for the finite element method, more likely than for the displacement method, we used the decisions got beforehand, and decisions as, for example, the magnitude of the elements of the stiffness matrix of each finite element, and we distribute the calculation of the mechanical system into the mechanical calculation of the each finite element. Usually we had before the decision of the mechanical issue. and the finite element method itself is just only the vector geometry matrix form of combining of the decisions had before for each element of the mechanical system, that is for each finite element, into the unit one discrete model. The matrix form is the product of the stiffness matrix on the displacements of the nodes of the ends in the coordinate system, local or maybe not local, maybe the global coordinate system of the depends what we look for the forces action on the mechanical system or action on the definite one finite element. The product of the stiffness matrix on the vector of displacements gives us the vector of the acting forces to the end of the finite element, if we consider the finite element in the local coordinate system. 4.6.5. Transition from the global coordinate system to local one associated with the finite element to find the displacement of ends of the finite element and its deformation, taking into account the direction cosines of local coordinate system in the global coordinate system. If we have the vector of displacement of the end of the finite element, so we can find in the global coordinate system, we can transform this vector to the local coordinate system by the multiplication of the vector of displacement in the global coordinate system on the cosine matrix. Cosine matrix is of the standard form for the flat approach of finite element method. Standard form is of two lines, usually for the truss, two rows of the cosine matrix and the four columns. Why the number of the rows is more than number is less than the number of the columns? Because originally this is two matrices of the cosines, and due to we have two ends of each finite element, each rod finite element, so the size of the matrix increases in the length of the rows. So we have two rows. Then the first row in the first column we have cosine, second element is sine, next two zeros, and the second row we have 0, 0 elements of the row of the second, and the last two elements of second row is cosine and sine of the inclination of a definite one finite element to the positive direction of the abscissa axis of the global coordinate system. 4.6.6 transposing a cosine matrix in Excel using the transpose function. We have to select by the mouse the place of the insert of the result of transposition of the matrix. Next, we have to dial in the address bar of the Excel the transpose function, and in the parameter of this transpose function we have to select by the mouse the range of the elements of the matrix to be transposed and insert it in the selected previously range of the cells of the Excel. 4.6.7 multiplying the transposed cosine matrix by the local stiffness matrix of a rod finite element in Excel using malt function, yes. First we have to transpose cosine matrix by local stiffness matrix, multiply by this function. To do that, we have to select the range of the insert of the cells of the matrix result of the product of two matrices. And next, when we select this interval of the insert of the result in the address bar of Excel, we have to apply for the function of alt, the product of the matrices, and in the parameters we have to indicate the intervals of the location of the elements on the Excel sheet, elements of Excel sheet of the matrices to be producted. The first matrix and the second matrix, the sequence of the product of the matrices is very important. 4.6.8 finding the stiffness matrix of a rod finite element by multiplying of transposed cosine matrix by the local stiffness matrix of the element and by the original cosine matrix. Yes, This is what is the transforming from the global coordinate system to local coordinate system. To do the reverse transformation of the stiffness matrix in the global coordinate system, we have to first to find the product of three matrices. The first matrix is the transposed cosine matrix. Second is the stiffness matrix of rod finite element in the global coordinate system. And the third matrix is the cosine matrix, but not transposed. So the first factor is transposed cosine matrix. The last factor is not transposed, usual cosine matrix. This multiplication in the Microsoft Excel is convenient to do consequently. So to find the intermediate matrix, next to find the product of intermediate matrix. Intermediate is a product of first two matrices, transposed cosine matrix on the stiffness matrix in the global coordinate system. And next, the usual cosine matrix as a second step. 4.6.9, the location of the stiffness matrix of rod finite element and the stiffness matrix of entire flat truss on a fragment of Excel page determined by node numbers. When we combining the stiffness matrices of each finite element determined in the global coordinate system into the stiffness matrix of the integral mechanical system, we have to have the template with the cells available for each node of the discrete model of the coordinate system of connection. Each in the template which consists the elements, the places for the elements for the each node of the discrete model of the mechanical system. And after that, we having the stiffness matrices of each finite element in the global coordinate system. We have to select and to copy the magnitudes of the stiffnesses of the elements of stiffness matrix of each finite element in the global coordinate system. We have to do the copies into the places in the template. Places available for this definite one node, which corresponds to the node of the stiffness matrix, corresponds to the elements of stiffness matrix we got in the global coordinate system. So this is like instead of the use of the incidence matrix of the correlation between the displacements of the nodes of the discrete model and between the ends of the finite elements connected in these nodes. This is a matrix of the incidence we considered in the article 4.4. 4.6.10, determination of the Excel program of the general stiffness matrix of a flat truss by adding the stiffness matrix of finite elements in the global coordinates. Yes, after the filling of the templates for the case of each finite element, we fill the template by the elements of the stiffness of each finite element from the matrices of stiffness of each finite element in the global coordinate system. After that, we can find the general stiffness matrix of a flat truss by adding the stiffness matrices of rod finite elements in the global coordinates. 4.6.11, adjustment of stiffness matrix elements considering the fixation of truss nodes. Yeah, we have, after finding the stiffness matrix of the mechanical system, we have to account the fixation of truss nodes. To do that, we have to find the nodes and the direction of displacement not allowed by the support fixation. In these definite cells in the stiffness matrix, we have to type 1, just a number 1, and all other elements in this column and in this row, we have to type 0. This is a fixation of truss nodes. Before the process of the stiffness matrix, keeping the process of the stiffness matrix when finding the displacements of the nodes. Finding the inverse matrix of the mechanical system in the Excel program using a M-inverse function. To find the inverse matrix, we have to select the range on the sheet of the Excel or the cells of the Excel to insert the the elements of the inverted matrix, and when we just indicate by the mouse this range of the cells, we can dial in the address bar of the Microsoft Excel the function of m inverse, and in the brackets we have to indicate by the mouse as well, or just by the typing, but maybe by the mouse we can select the matrix to make inverse, and it will be inverted and inserted in the previously defined range before the dialing of the command of m inverse in the address bar of Excel. 4.6.13 determination local displacement of mechanical system nodes based on the found global displacements. Transition from the global system to local one to find displacements of coordinate systems associated with the finite rod elements. When we got the displacements of the ends of finite elements in the global coordinate system, we can and we have to first transform this displacement to local coordinate system by the product of vector of displacement of mechanical system nodes. Mechanical system nodes is the discrete model. First, we have to find the product of displacement of the of vector of displacements of the mechanical system nodes in the global coordinate system by the matrix, by the cosine matrix. Not transformed, but the usual, not transposed, but the usual cosine matrix. And we will have the vector of the displacements in coordinate system associated with the rod elements that is in the local coordinate systems. It's important because if in the next we have to find the deformation, the relative displacement of the ends of the mechanical system finite element, the local coordinate system, we have to transform first the vector of displacement from the global coordinate system to the local one. 4.6.14 finding the deformations of the rod finite element of a mechanical system and the stress acting on the finite elements in Excel program. It is easy to do because to do that we have to subtract to find the deformation having the displacement of the end of the finite element in local coordinate system. To find the deformation we have to subtract from the displacement of the end of finite element we have to subtract the displacement of the beginning of the finite element, and this difference of the displacement of the end and the beginning of finite element we have to divide by the length of the finite element, and we will have the deformation of definite one finite element. Even the deformation with the absence of the distributed load in accordance with the concept of finite element method, this information is even distributed along this each one definite finite element. And after that we can find the mechanical stresses within the finite element by the for the truss, just when we consider only stretched or compressed finite elements. This is the product of the deformation of finite element by the modulus of the elasticity of finite element. We will have the stresses acting in the transverse section of finite element. After that, we can find the forces acting in the finite element, stretching or compressing forces by the product of stresses on the transverse section area of finite element. Thank you.